Welcome. In this session, we'll be discussing problem number 217, contains duplicate. This problem is a classic example of working with arrays and hash maps, a core concept in programming. We'll explore a few approaches to solve it, starting from brute force and moving towards more efficient solutions. Let's dive in. In this problem, we are tasked with determining whether any value in a given integer array appears at least twice. If there is at least one repeated value, we return true. Otherwise, if all the elements are distinct, we return false. The input to our function is an integer array called nums, and the output is a Boolean value. For example, if the input array is 1, 2, 3, 1, we can see that the value 1 is repeated. Therefore, the output for this input would be true. This forms the core of the problem we need to solve. Now, let's explore the output for the first example. When the input is nums equals 1, 2, 3, 1, the output is true because the value 1 appears more than once in the array, specifically at indices 0 and 3. This confirms that there is a duplicate. In the second example, the input is nums equals 1, 2, 3, 4. Here, all the values are distinct, which means there are no repeats. Consequently, the function returns false as the output. Expanding further, the explanation for the second example emphasizes that every element in the array is unique. Therefore, the output remains false. In the third example, the input array is nums equals 1, 1, 1, 3, 3, 4, 3, 2, 4, 2. Here, not only does the value 1 appear multiple times at indices 0, 1, and 2, but the values 3 and 4 also appear more than once. Because of these repeated values, the function returns true for this input, highlighting the presence of duplicates. Now, let's consider the constraints and some edge cases. The array can have a length ranging from 1 to 10^5, and each element in the array can have a value between -10^9 and 10^9. For edge cases, if the array contains only one element, such as nums equals 1, the output is false because a single element cannot have duplicates. Similarly, if all elements are distinct, like nums equals 1, 2, 3, 4, 5, the output is also false. However, if all elements are identical, such as in nums equals 2, 2, 2, 2, the output is true because the value 2 is repeated multiple times. Finally, we need to ensure that our solution handles large inputs efficiently. For example, if the input array has a size of 10^5 with random values, the algorithm must perform well within these constraints. This makes it crucial to choose an approach that can process the data in a time-efficient manner, ensuring we meet the requirements for both correctness and scalability. To start, let's consider the brute force approach. Here, the intuition is straightforward. For each element in the array, we compare it with every other element that comes after it. If we find a match, we immediately return true, indicating that duplicates exist. Otherwise, if we go through all the comparisons without finding any duplicates, we return false. While this method is simple and easy to implement, it has a significant drawback. Since we're iterating through the array with nested loops, the time complexity is O(n squared, which grows very quickly as the size of the input increases. On the other hand, the space complexity is O(1), because no additional data structures are used. This makes the brute force approach impractical for larger datasets, as the computations become too expensive and time-consuming. Now, let's explore a more efficient method using a hash set. The intuition here is that a set inherently stores only unique values, making it a great tool for detecting duplicates. As we iterate through the array, we add each element to the set. If an element is already in the set, we immediately return true, because we've found a duplicate. If the loop finishes without finding duplicates, we return false. The key advantage of this approach is its efficiency. A hash set provides constant time operations for inserting and checking the existence of an element on average, which eliminates the need for nested loops. This significantly reduces the time complexity to O(n), making it much faster for larger datasets. The time complexity of the hash set-based approach is O(n), because we traverse the array once, performing O(1) operations for each element. However, the trade-off is in the space complexity, which is O(n) as well. This is because, in the worst-case scenario, where there are no duplicates, the set will grow to the size of the input array. Nonetheless, the drastic improvement in time complexity makes this a worthwhile trade-off for larger datasets. Another approach to consider is sorting the array. If the array is sorted, duplicates will appear as consecutive elements, so we can simply compare each element with the one next to it. If any two consecutive elements are the same, we return true, otherwise, we return false. This approach eliminates the need for additional data structures, but the time complexity is O(n) log n, due to the sorting step, which is slower than the hash set approach. Sorting the array has a time complexity of O(n) log n, because the sorting process dominates the performance. The space complexity depends on the sorting algorithm used. If the array is sorted in place, the space complexity is O(1). However, some sorting algorithms might require additional space, making the space complexity O(n). While sorting is less space-intensive compared to the hash set approach, it modifies the input array, which might not be acceptable in certain scenarios. For our chosen strategy, we opt for the hash set-based approach. It strikes the best balance between efficiency and simplicity, with O(n), time complexity and manageable space usage. Although it requires additional memory, the significant time savings make it the optimal choice for most use cases, especially when handling large datasets. The sorting and brute force methods, while valid alternatives, are less optimal due to their higher time complexities and, in the case of sorting, the potential modification of the input array. The problem requires us to determine whether any value in an array of integers appears more than once. If a duplicate exists, we return true, otherwise, we return false. To begin, let's explore the brute force approach. This method systematically compares each element in the array to every other element. First, we initialize an outer loop, starting with the first element, nums I. This loop runs from index 0 to n2, where n is the length of the array. We stop at n2 because the last element will have already been compared to all prior elements during earlier iterations. The purpose of this loop is to ensure that every element in the array has a chance to be compared against all others. Next, we introduce an inner loop that begins at i+1 and goes up to n1. This inner loop allows us to compare nums I with all subsequent elements in the array, ensuring no redundant or self-comparisons occur. This structure ensures all necessary comparisons are made in a systematic way. Within the inner loop, we check whether nums I is equal to nums j. If a match is found, we immediately return true, as this confirms the presence of at least one duplicate in the array. There's no need to continue further once a duplicate is detected. If the inner loop completes without finding a duplicate, the algorithm moves to the next iteration of the outer loop, selecting the next element in the array for comparison. This ensures that every element is thoroughly checked against all others. Finally, if both loops complete and no duplicates are found, the algorithm returns false. This result indicates that all elements in the array are distinct. While this approach is straightforward and ensures a complete search, it is not the most efficient method, as it requires a nested loop structure to perform these comparisons. Analyzing the brute force approach reveals some important insights. The time complexity of this algorithm is O(n) squared. This is because for each iteration of the outer loop, which runs n times, the inner loop runs approximately n/2 times on average. As the array size grows, this quadratic growth in comparisons makes the approach inefficient. In terms of space complexity, it is more favorable, requiring only O(1) additional space since no extra data structures are used. This simplicity is a key strength of the brute force method. It is easy to implement and understand while avoiding additional memory usage. However, its inefficiency for large arrays is a significant drawback, particularly in performance-critical scenarios. Overall, while the brute force approach can be useful in small-scale problems, its limitations become apparent as the input size increases. To improve efficiency, we can explore alternative methods. One popular optimization involves using a hash set. By traversing the array and storing each element in the set, we can check for duplicates in constant time. If an element is already present in the set, we return true. This approach reduces the time complexity to O(n), though it requires O(n) additional space. Another option is to sort the array first. After sorting, duplicates can be identified in a single pass by comparing consecutive elements. While sorting has a time complexity of O(n) log n, it eliminates the need for nested loops. Both methods represent significant improvements over the brute force approach. Additionally, it's important to consider edge cases. For example, an empty array or an array with only one element should return false, as duplicates are not possible. Arrays with all unique elements or all identical elements must be handled correctly as well, ensuring the algorithm consistently produces accurate results. To illustrate how the brute force approach works, let's walk through an example. Consider the input array nums equals 1, 2, 3, 4, 1. The outer loop begins with I equals 0, setting nums 0 equals 1 as the current element. The inner loop then compares nums 0 with nums 1 equals 2, nums 2 equals 3, nums 3 equals 4, and finally nums 4 equals 1. At this point, a duplicate is detected, and the algorithm immediately returns true. Now, for a different array, such as nums equals 1, 2, 3, 4, the outer loop compares each element with all subsequent elements. Here, no duplicates are found after exhausting all comparisons, so the algorithm returns false. These examples demonstrate how the brute force approach systematically examines the array to determine whether duplicates are present. The solution to the contains duplicate problem involves checking whether any number in the input list appears more than once. To achieve this efficiently, we use a set to keep track of numbers we have already seen as we iterate through the list. The function contains duplicate begins by initializing an empty set called scene. A set is chosen because it allows for fast lookups and insertions, both of which are average O(1) operations. This choice ensures the algorithm remains efficient compared to other potential data structures. Next, we loop through the input list nums. For each number in the list, we check if it is already present in the scene set. If it is, this indicates that the number is a duplicate, and we immediately return true. This early exit ensures that we stop processing as soon as a duplicate is found, saving unnecessary computation. If the number is not in the set, we add it to the set. This ensures that for subsequent iterations, the current number will be recognized as a duplicate if it appears again. If the loop completes without finding any duplicates, the function returns false, indicating that all the numbers in the list are distinct. This approach is both time and space efficient. The time complexity is O(n), where n is the length of the input list, because each element is processed at most once. The space complexity is also O(n) in the worst case, as the scene set may need to store all unique elements from the input list. In summary, this solution strikes a balance between simplicity and efficiency, leveraging the properties of sets to solve the problem in linear time. This is the Java implementation of the contains duplicate problem, which mirrors the logic of the provided Python solution. The code uses a hash set to track scene numbers and determines if any duplicate exists in the input array. Key differences between the Java and Python versions include explicit type declarations for variables, the use of Java's hashset from the java.util package, and the standard Java class structure. To solve the problem of detecting duplicates, we start with the first example where the input is nums equals 1, 2, 3, 1. The process begins by initializing an empty set called scene. This set will help us keep track of the unique numbers we encounter. Now, in the first iteration, we look at the number 1. Since 1 is not in the scene set, we add it, and the set becomes 1. In the second iteration, we encounter the number 2. Again, it's not in the set, so we add it, and the set updates to 1, 2. Next, we process the number 3, which is also new, so it gets added to the set, making it 1, 2, 3. Finally, in the fourth iteration, we encounter the number 1 again. This time, it's already present in the scene set, which means we've found a duplicate. At this point, the function returns true because the input list contains a duplicate number. In this example, you can visualize how the scene set grows after each iteration as unique numbers are added to it. The moment a number is encountered for the second time, like 1 in this case, the function immediately identifies it as a duplicate and returns true. Now, let's consider another example where the input is nums equals 1, 2, 3, 4. We begin by initializing the scene set as empty. In the first iteration, the number 1 is not in the set, so we add it, resulting in 1. In the second iteration, the number 2 is also not in the set, so we add it, making the set 1, 2. Then, we process the number 3, which is also unique, so it's added to the set, updating it to 1, 2, 3. Lastly, we process the number 4, which is again not in the set, so it gets added, and the set grows to 1, 2, 3, 4. After processing all the numbers in the list 1, 2, 3, 4, the scene set contains all the unique elements from the input. Since no number is encountered more than once, there are no duplicates. The function performs a final check and confirms that no duplicates were found, so it returns false. Now, let's analyze another example, nums equals 1, 1, 1, 1. We start by initializing the scene set as empty. In the first iteration, the number 1 is not in the set, so we add it, and the set becomes 1. In the second iteration, we encounter the number 1 again. This time, it's already present in the set, meaning we've found a duplicate. As soon as a duplicate is detected, the function returns true without needing to process any further numbers. In this case, the scene set only contains the number 1 after the first iteration, and the second iteration immediately reveals the duplicate when 1 is encountered again. This approach highlights the efficiency of using a set for this problem. The function works by leveraging the constant time membership checks of a set. As we iterate through the list, we check if the current number is in the set. If it is, we can instantly return true. If it's not, we add it to the set and continue processing. If the loop finishes without finding a duplicate, we return false. This method is efficient because it processes each number only once, giving it a time complexity of O, n, where n is the length of the input list. The space complexity is also O, n, since the set only stores unique numbers from the input. This balance of time and space efficiency makes the approach well suited for solving the problem. We start by analyzing the time complexity of this solution. The algorithm goes through the input array, nums, using a single for loop. Let's say the array has n elements. Each iteration of the loop processes one element, and since it executes exactly n times, this contributes O, n, to the time complexity. Inside the loop, we perform two operations involving a set, checking if an element exists in the set and adding an element to it. Both of these operations have an average time complexity of O, 1, because sets are implemented as hash tables, which allow for efficient lookups and insertions. Since these operations are performed for each of the n elements, their combined contribution is O, n, asterisk O, 1, which simplifies to O, n. Adding it all together, the overall time complexity of the algorithm is O, n. Now let's examine the space complexity. The primary contributor here is the scene set that we use to track the elements we've encountered. In the worst-case scenario, when there are no duplicates in the array, the scene set will need to store all n elements. Since each element is stored exactly once in the hash table, the memory usage is proportional to the number of unique elements, giving us a space complexity of O, n. Apart from the set, the algorithm uses a constant amount of additional space for variables like number and the scene set itself, which contributes O, 1, to the space complexity. When we combine these, the overall space complexity of the algorithm is O, n. Let's break down the different cases for this algorithm. In the best case, a duplicate is found very early, such as at the second position in the array. Here, the algorithm terminates early, so the time complexity is effectively O, 1. However, the space complexity still remains O, n, in the worst case, as the scene set could still grow depending on the input. For the average case, the algorithm typically processes most of the elements in the array before finding a duplicate or reaching the end of the array. The time complexity in this scenario remains O, n, and the space complexity is also O, n. In the worst case, where all elements are unique, the algorithm iterates through the entire array, and the scene set grows to the size of n. This results in a time complexity of O, n, and a space complexity of O, n. Comparing this to a brute force approach, where we would use nested loops to compare every pair of elements, the naive method has a time complexity of O, n squared, and a space complexity of O, 1, since it requires no additional data structures. The optimized approach with a set drastically improves the time complexity to O, n, with a trade-off of using O, n, space. Finally, let's prove the big O complexities more formally. For the time complexity, we process each element in the array exactly once, giving us n iterations. Since each iteration involves two set operations, membership check and insertion, that both have an average time complexity of O(1), the total time complexity becomes O(n) asterisk O(1) equals O(n). For the space complexity, in the worst case where all elements are unique, the scene set grows to store all n elements. Each element requires constant space, so the total memory usage is proportional to n. This means the space complexity is O(n). These proofs confirm that the algorithm is both time and space efficient given its constraints. One of the most common mistakes when solving this problem is overlooking edge cases. For example, what happens when the input array is empty, has just one element, or contains all identical elements? Forgetting to account for these scenarios can lead to incorrect outputs or runtime errors. The solution is simple: always test your code explicitly with such edge cases to ensure correctness. Another mistake occurs in brute force approaches, where developers might accidentally compare elements with themselves or check pairs that have already been visited. To avoid this, make sure your inner loop starts from the next index, not the beginning of the array. Additionally, when using optimized solutions like hash-based approaches, it's important to consider space complexity. For very large datasets, the memory overhead of a hash table can become significant and exceed problem constraints. A good practice is to weigh the trade-offs between time and space efficiency. Lastly, some may assume that sorting alone guarantees correctness. However, sorting only works if you explicitly check adjacent elements for duplicates. Always validate your logic after sorting to ensure accurate results. Another issue to watch out for is the performance of hash-based solutions. While they are efficient, hash operations can become slower as the hash table grows larger, especially in edge cases with high input sizes. To mitigate this, consider the problem constraints before relying on hash-based methods. From an interview perspective, it's essential to clearly articulate why you chose a specific approach. Be prepared to discuss trade-offs, such as the time complexity of O(n) squared for brute force methods versus O(n) log n for sorting, or O(n) for hash-based solutions, and how space complexity plays into your decision. Always analyze the problem constraints, like array size or value range, to choose the most efficient solution for the given context. When explaining your solution, highlight how you've handled edge cases, such as empty arrays or arrays with all identical values, as interviewers often focus on these details. Additionally, be flexible in your approach. Problems may be modified to require unique duplicates, counts of duplicates, or even the indices of duplicates. Show that you're ready to adapt your solution to such variations. This problem has several related variations that are worth exploring. For example, contains duplicate 2 asks you to find duplicates within a specific index range, while contains duplicate 3 introduces both value and index range constraints. Another closely related problem is single number, where you need to find the one element that appears only once in an array where every other element appears twice. As for solving strategies, there are multiple approaches you can take. The brute force method, which compares each element with every other, is straightforward but inefficient for large arrays due to its O(n) squared time complexity. It has the advantage of not requiring additional space, though. A more efficient solution involves using a hash set. By storing elements as you iterate, you can achieve O(n) time complexity, but this comes with an O(n) space requirement. Another approach is sorting the array, which reduces space requirements to O(1) if done in place. After sorting, you only need to check adjacent elements for duplicates. This method is slower than hash-based solutions, with a time complexity of O(n) log n, but it's a viable alternative when conserving memory is a priority. For certain problem types, bit manipulation techniques can offer an elegant and efficient solution. For example, XOR operations are particularly useful in problems like finding a single number in an array, where every other element appears twice. The XOR operation takes advantage of the property that a number XORed with itself results in 0, and a number XORed with 0 remains unchanged. This allows you to isolate the unique element in linear time while using constant space. However, it's important to note that this approach has limited applicability. It works well in scenarios designed for XOR-friendly operations, but it doesn't generalize to all problem types. When considering alternative approaches, always assess whether the specific characteristics of the problem align with the strengths of bit manipulation techniques. Great job! We've successfully tackled problem number 217, contains duplicate. Today, we learned how to approach this problem using both brute force and efficient hash-based methods. Don't forget to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!